Alla Detinko from the University of Huddersfield, here to talk to us about algorithms for the Zariski dense subgroups and their applications.
Thank you very much. Thank you for introduction. And I'm very grateful for organizers to give me a chance to present here this area of research. It's a new area. And this is a joint project with my collaborators, Dane Flannery from National University of Ireland and Alexander Hulpke from Colorado State University. And probably the main reason why I'm here, this is another area of research, interest of Misha Kapovich. And some of applications which I selected from this talk came from our collaboration with Misha. Let me start with a very brief introduction, not into this entire area, but in small piece which can be of interest for geometry. So this research you can guess, this is not geometry. This is area which sometimes these days is called computational algebra. And moreover, within computational algebra, this is quite novel domain. So what this research is about? Our aim is to design a set of practical algorithms to handle matrix groups over an infinite field. I would expect that at least some of you have been using computer algebra systems in your research. GAP, Magma, maybe something else. Some of you maybe contributed even as developers. So you can be aware that very similar machinery for permutation groups and finitely presented groups. Our aim is to design similar machinery for matrix groups over infinite fields. What is the motivation for this research? Well, no need to explain for this audience why linear groups are important. You are using them for representation of groups which you apply in geometry or other geometrical objects. And our motivation is solution of mathematical problems by computer experimentation. Not by classical methods, professorium. No, this is something else. This is different type of research, and this is not even mathematics. This is interface of mathematics and computer science. Well, I just mentioned that for permutation groups, for finitely presented groups, there are a set of functions, there are theoretical algorithms, there are practical implementations. So why the case of linear groups over infinite fields, despite of importance, was missing? Well, this is challenging area. First, some fundamental algorithmic problems are undecidable, or it is not even known whether problems are decidable or not. And later I will show you such problems. Another issue is complexity. We are over infinite domain. And after a few steps of computing, you can run into, for example, such issues that growth of matrix entries. And algorithm will not work. It is considerable distance between algorithm which perfectly work on list of paper and algorithm which work in computer. And another problem is there is no methodology how to compute these groups. There are algorithms for finitely presented groups, which potentially can be infinite. But linear groups, even finitely generated, are not necessarily finitely presentable. Moreover, if they are finitely presentable, to find presentation, it's not straightforward. But even if you have a presentation and you apply algorithms for finitely presented groups, again in practice, they may not work because of complexity issues. In few steps, you can run into growth of matrix edges. So that was motivation for our research. So few further comments why actually linear groups. Again, no need to explain for you why linear groups are important. This is what is commonly used in not only in geometry, in algebra for representation of algebraic structures of various mathematical objects. What is probably less known, that matrices are a very convenient way to represent mathematical objects on computer. What I mean, input of very small size can designate huge mathematical object, even infinite mathematical object. For example, 50 bytes is enough in order to input SLNZ in computer. You can consider it as an exercise. So, I mentioned, yes, linear groups are important. Why finitely generated linear groups? There are several issues involved. First, to input your group, you need a finite set. And an obvious selection would be finite set of matrices. This is one reason why we ended up with finitely generated groups. Probably a quick comment, you actually can represent groups on computer using other finite set of polynomials. You will end up in computing with algebraic groups. There are algorithms in that area, they are closely related to what we are doing, but nevertheless, we are working with finitely generated groups. And there is something else special about finitely generated linear groups. Few remarkable properties which make these groups very convenient for computing. First property. These groups are residually finite. Old classical results goes back to Fortis to Hansen. But this is very efficient from computational point of view. So, finitely generated groups are approximated by matrix group of the same degree of finite fields. And this provides reduction of computing from infinite field to finite field. So this addresses such issue as complexity. And another issue of reduction to groups of finite fields. This is quite well-developed area of computational group theory. There are quite efficient practical algorithms to handle matrix group of finite fields. So this is another advantage why it makes sense to take finitely generated linear groups. How efficient would be this approach? This is computer realization of finite approximation. One congruence quotient is enough in order to recognize whether the group is finite or infinite. So, quick comment. In a class of finitely generated linear groups over infinite field, any infinite field, zero positive characteristic, finiteness is decidable. And you can recognize this property within just one congruence quotient. So why Zariski density? How Zariski density came into the game? How we perform actually computer experimentation with finitely generated groups? What do you need? Which algorithms do you need? So it is recognition of properties, investigation of structure, but if we want to proceed with congruence quotients, we will have two issues. Given an arbitrary finitely generated linear group, can we actually find all congruence quotients? One issue. And another issue is to which extent congruence quotients define the group, properties of the group, structure of the group. And this is how Zariski density came into the game. For illustration, let me take SLN Z. This is the simplest case to illustrate, but the same idea is applicable for other classes of groups and other domains. So SLN Z has two remarkable properties. First remarkable property is the strong approximation. This property tells us that if group is Zariski dense, that almost all congruence quotients are SLN P for prime P. There is just finite set of exceptions for which dense subgroup does not surject on SLN P. This addresses first issue, whether it is feasible to describe all congruence quotients. Still not clear how. And the second remarkable property for SLN Z, at least for n greater than 2, is congruence subgroup property, which describe the structure of finite index subgroups. So arithmetic subgroups are finite index subgroups of SLN Z. And according to congruence subgroup property, another fundamental result from arithmetic set of algebraic groups, each arithmetic subgroup is congruent subgroup, which contains the kernel of reduction modular some positive integer, and moreover with positive integer maximal one, the smallest one, is unique. So whereas uniquely defined maximal principal congruent subgroup in any finite index subgroup of SLN Z. So how these two properties will come into the game? This suggests the scheme for computing. So again, let me repeat. Which algorithms do we need? What you have in practice in computer experimentation is a handful of square matrices over some domain, infinite field or infinite ring. The question, if you want to solve mathematical problem using this model, which algebraic object with finite set of matrices designate, recognize the type of the group, and investigate structure and the properties of this group. So one reason why I selected SLN Z for illustration is that this is the most developed case, which is all algorithms have been not just developed, they have been implemented, tested, and publicly available for free. So this is where you can find them, including the manual, And I will use terminology which came from implementation to illustrate terminology. I mean name of function. So you have finite set of matrices. First question to be answered. Is a group dense? Here density means in Zariski topology. And since I consider subgroups of SL and Z, it's density in SL. Well, the same way you can test density in other groups. Separate question. Next question, which we will do computationally. If group is dense, it satisfies a strong approximation property. It's surject on SLNP, well, must all primes P. This function, primes for dense, compute with finite set of exceptional primes. Compute the set of primes for which H does not surject on SLNP. So what this gives us? In fact, the set of all congruence quotients modular primes, because we have just finite set of exceptions, which we can explicitly calculate. And out of this finite set, congruence quotients are SLNP. And the most sophisticated part of computing is function which is called level max PCS, level of maximal principal congruence subgroup. So what we're computing here is so-called congruence closure. So what is congruence closure? For SL and Z, for n greater than 2, this is the smallest arithmetic over group, which contains your finitely generated group H. This is a simpler situation. In fact, function will work in more general settings. As I mentioned, algorithms available for other groups and for other domains, and later, when I will proceed with applications in geometry, we will consider different domains. So this is a very brief introduction into this area.
Should do something for finite index subgroups H.
Say it again?
Are you assuming that H has
No,
finite
we
index?
don't know. Given it, no. What I assume group is dense. I don't assume I will, give me 5 minutes, you will see. Well, I will, this is vital question. In general, this is not decidable problem, it's semi-decidable problem. Given subgroup, to decide whether it is arithmetic or not. And we don't assume that the group is arithmetic. In most of cases, it is impossible even to answer this question. And nevertheless, even if group potential is of infinite index, we still can compute with it and answer various questions. In 5 minutes, you'll see. So, few details. Density is quite big property, quite easy to test. And we have several algorithms to test density. Again, one congruence quotient is enough to recognize whether the group is Zariski dense. Alternatively, you can use joint representation and something a little bit more exotic, which is Monte Carlo algorithm by Igor Riven. It's extremely efficient, and again, it is implemented. So, what we have is computational realization of the strong approximation property. So we have algorithm, which for dense subgroup calculate with set of exceptional primes. Very similar research, so-called quantitative strong approximation theorem. This is a set of asymptotic bounds on a set of primes. So how these two results are related? You don't need any asymptotic bounds. It's nice to have them. The best, which I know due to Briard, which is our algorithm output explicit set of primes, whether it is just one prime or 1 million primes, or the answer is that groups surject modular all primes. Very useful to test profinement density. So, and this mysterious group, which I called congruence closure, this actually, in other terminology, extended congruence subgroup. This construction initially was introduced by Peter Sarnak, and when full justification of existence was provided by Vienke, 1999. So this is just few details again. This is very brief introduction. I know you are geometers. You are sitting and thinking what we can get from that. So let me proceed with applications. So I selected for illustration how this method works, just few applications. And what is of interest for you, especially for new generation, for students which are here, status obvious problems still were open. So, all right.
Can I ask you, P0 and C0 independent of n?
Here, this one.
Yes.
I should check. Maybe I misprinted, but I think I will check. I have it on my computer with paper. Well, it is in terms of, I also surprised because he used a joint module to justify. And his bound is in terms of entries of generators. Anyhow, this is not my result. This is just an illustration.
One is applying also for algebraic groups of the Q, other like S of the Q, for instance, or just the specific Russell and Bar?
Well, all right. We have finitely generated group. Initially, it is over infinite field. But since group is finitely generated, it is automatically designated over a ring. What is the ring? It is a ring, it's finitely generated integral domain. This is vital. It is a ring generated by entries of generating matrices. And what is this finitely generated domain? So if you take subgroup in SLNQ, and if this group is finitely generated, that in real life, it sits here. It will be over localization of that. And this is why the method works. Initially, it is over infinite field, not necessarily rational, it can be any. But it will be over finitely generated integral domain. This is over ring. This is why we have finite approximation property. This is the background of finite approximation. And this is actually where commutative algebra comes into the game, into justification. So I'm hurry up to show you applications. Well, again, this introduction is very short. I did not give you any mathematical background to this method. This is a separate story. I think this is not what you are interested in. the geometries you are interested in applications, what you can get from that. So a few open questions for you, which I selected for this talk. So first problem which I wanted to use is self-reset challenge. So what the problem is about? Let's just take, what can be simply self-reset? So let's just take finitely presented group, and let us consider representation of this group. And what is known about this representation is that it is Zariski dense for any parameter k from images. This is result by Darren Long and Alan Reed. And at the top of that, we managed to justify that for few values of k, this group is even arithmetic. This is theoretical justification. We use Bianchi criterion on arithmeticity, very popular, published in 1987. This is not what is the story about. Why we actually constructed this representation? What is the point? Well, it's quite well-known open problem, long-standing open problem. This is Hausen property and coherence for self-reset. It's quite well known that if n is different from 3, that for n equals 2, well, SL2Z is both has Hausen property and is coherent simply because it is virtually a free group. It's not very difficult, but not straightforward actually, to prove that if n is greater than 3, we have negative answer. So the question is, what is about n equals 3? And that was the motivation for this construction by Long and Reed. Again, the background for this construction came from low-dimensional topology. It's very interesting work. But anyhow, this is where we stopped. We managed to justify Zariski density. It's quite easy to test. By the way, you can now, for an arbitrary k, can answer this question computationally, just input it to our algorithms. And we prove arithmeticity. So, as I told you, the status of this problem is still open. The problem we run into, what are actually these groups for the values of parameters of k? What is the structure of these groups actually? This is not in general fightful representation, or even not known for various values of k, whether representation is fightful or not. Sometimes our methods answer this question, at least if we have arithmetic representation, but in general it's not known. How to proceed? So let us apply to this problem our computational machinery to see how it works and to answer probably the main question which you have on your mind. Do we really need it? Do we need a computer to answer these questions? So, how our computational scheme will work? So, no need to test density. It has theoretical justification, but if you're curious, you can do it. I told you, the Zariski density is quite straightforward to be tested. So we start with computing with primes for dense, set of primes for which we don't have subjection. This is again and again computer realization of the strong approximation theorem, one of the fundamental theorem of arithmetic theory of algebraic groups. When we compute congruence closure, what is congruence closure? The smallest arithmetic over group. And as soon as we have it, we will be able to answer at least some questions on the structure of the row K groups and how they sit in SL3Z. In particular, we will be able to answer the question what actually is the index of congruence closure. Congruence closure is arithmetic subgroup. It is a finite index. Original subgroup H, we don't know. So this is just a sample of experimental output, just to illustrate. That was one of the first experiments which we ran. In particular, we used that construction by long read to test our software, to test its practicality. Because theoretical complexity, about which it was few talks here, and practicality is not the same. It's quite different things. So, well, if you wonder why I ended up here with k equals 20, just for illustration, you can take k equals 100, 1000, whatever. It does not make any difference. So what is experimental output? This column gives us this congruence closure. Smallest arithmetic overgroup. And last column is the index of congruence closure. Quite large indices. Well, few comments on this experimentation. How long does it take to answer these questions? 15 minutes of computer time. I did not include on my slides all information. In particular, what we can find, the set of all congruence quotients. Given a finitely generated Zariski dense subgroup in SL3Z, we can find all congruence quotients. No need to explain for people who are working in this class of groups how I apologize. Point of view of applications. And last comment. There is no any other methods to answer these questions, in particular to compute indices. There are classical methods such as cassette enumerations. Go ahead, try it, and long and read actually try it. No, nothing else will work. This is what I mentioned at the beginning. Motivation to develop algorithms specifically for linear groups, because cassette enumeration is technique for finitely presented groups. Doesn't work. Yes, this is what I just told you. We don't use cassette enumerations. Completely different technique. Mathematics behind this is quite heavy. But in practice, just go ahead and use it. So, as I told you, I selected just a couple of applications for illustration. Now, let us move to a completely different problem. Again, problem is still open. And this problem is open to work. And you can see that this problem, which I will consider now, has completely different flavor. So let's just take two matrices. Sometimes it is called parabolic Möbius groups, generated by opposite parabolics. Quite loose terminology, but. And let's just consider the following problem. For each rational x from interval 0 to, this group is free. Or can we actually decide non-freeness of the group? Y rational x and yx from this interval 0 to. Because for other x, the answer is no. Again, this is similar to a SL3Z challenge. if you take any x, complex x, such as absolute value is greater than 2, group is well known. It's free. Let's go back to Sanov and when a lot of other authors contributed into this problem for transcendental x. Spring. If you take algebraic non-rational, you also can readily give examples of free groups. So this is only remaining case. And it is remaining for quite a long time. Bibliography on this problem is absolutely enormous. At some stage I started to collect it, impossible, it's hundreds of papers, but approach general is number theoretical. It's quite easy to reduce it to the Fontaine equation and when apply number theoretical approach. Can we actually input this problem into our machinery? Let us see. Can we use Zariski density? And if so, how that will look? Let us consider this problem from group theoretical point of view. So I take rational m. Parameter x, I denoted it by m, it's rational. So I can consider it a subgroup of SL2 or localization of that. And it's quite easy to justify that arithmetic subgroups of this group are non-free. Why? Because in contrast to SL2Z, this group has congruent subgroup property. So how we can use it? How we can justify it? Take rational m from interval 0, for which it is not known whether the group is free or not. If you manage to justify arithmeticity, you will justify that group is not free. As simple as it. Well, it's simple to say, but very difficult actually to make it to work in computer, because here, for a change, to test arithmeticity, we use presentation of this group. Construction of presentation, in particular for composite denominator, is not straightforward problem. If you want to have algorithm which will work in computer, constructing this presentation. Anyhow, my collaborator Alexander Hultke solves the problem. So it is implemented. So we have a method. We have a presentation of SL2 localization Z. And if we want to justify non-freeness, let us show that group is arithmetic. So what is the outcome? We already got new values of rationals between 0 and 2, for which group is non-free. Moreover, in fact, it is infinite series of rationals, because if you have one, you can construct from infinitely many. Before us, other authors managed to get blind theoretical methods. Going back to Linden, and you can even, in the book of Linden and Shoup on combinatorial group theory, you can see this problem with discussions and some outputs. What we managed to justify, approaching this problem from group group theoretical point of view and using our machinery is that known non-free subgroups actually are arithmetic. Additionally, we got very important group theoretical information on the structure of these Möbius groups, which is the set of primes for which we don't have surjection and the smallest arithmetic overgroup. What is the congruence closure? So here is problem for your attention. We don't have any examples of thin non-free subgroups. So there are a lot of examples on non-free subgroups. For many of them, we can show that we are arithmetic. We don't have even one example of thin subgroup. Well, what I forgot to explain for you, maybe you never run into this terminology, which is in subtitle, arithmetic versus thin. Given the Zariski dense subgroup of SLZ, arithmetic is finite index. Thin is of infinite index. Well, this terminology was suggested by Peter Sarnak. In 2012, he published preprint, quite well known, where he collected a set of open problems from different areas of mathematics, including geometry, low-dimensional topology, theoretical physics, quantum computing, well, and group theory, which can be stated in terms of arithmetic versus thin. You did not know about this preprint. We came from this alternative arithmetic versus thin from our computational point of view, and nevertheless, we applied our methods to many problems listed by Peter Sarnak, including symplectic monodromy groups. These are groups linked to Calabi-Yau manifolds, and they came from theoretical physics, from string theory, second type of string theory. This is a separate question. This is not what I am talking about. So I selected just two problems to illustrate how method works.
Can I just ask about this remark? Is that just in PSL2Q, or is that in any arithmetic? There are no known examples in any arithmetic.
Let me tell you, because maybe he will suggest solution. What we have, I'm not joking, I'm quite serious. So what we have is this. So I consider it a subgroup here. So I know that this group is not free. Not by my methods, other authors. I told you, take a well-known book by Liden and Schupp, you will see a special section dedicated to this problem. We have examples of arithmetic subgroups here for selection of A and B. So what is the question about? We don't know even one example of non-free thin subgroup, which is non-free but of infinite index here. This is what is missing.
I see. So all the non-free subgroups you could apply your methods to turned out to be arithmetic and not thin.
No.
Oh.
For many of them.
Or for the ones you could.
For many of them, we know that we are arithmetic.
Yeah.
But we don't have examples of thin. Why? Thinness is undecidable. This is where you can come into the game. There is no proper mathematical justification that thinness is undecidable. Yes.
Are they always Zariski dense?
Yes. Yes.
For whatever A and B, they are always Zariski dense.
Well, maybe you can. You say we surject for almost all prime. If we surject for at least one prime, maybe these are Zariski dense. which is maybe there are some pathological exceptional cases, but in general, anyway, are Zariski dense.
Well, they're always Zariski dense. There are no exceptions.
Who's talking?
They're always, these particular groups are always Zariski dense.
I just told him that he can ask questions before power to figure out.
No, well, all right. So I promise you, which is applications in geometry, and at the last moments of my talk, I come to this point, which is applications in geometry. Which is well, in geometry, I think you are interested not for computing over Z. You rather would prefer to handle groups over number fields. And computationally, it is actually a huge distance from computing over Z to computing over number fields. And actually, this came from our collaboration with Misha Kapovich. Several years ago, we had joint program at ICERM, at Brown University. And this is where we started some discussions. So what I selected here for my talk is a sort of simplest case, but everyone's favorite group, it's Bianchi groups. I want to show you how our machinery come into the game. This is notation. So what I have is finitely generated subgroup. Well, I can consider not projective special linear group. For a moment, I just consider it. So how our computational methods will come into the game? How we will modify our scheme for computing? Well, start point is to test density. In degree 2, our algorithm is actually much simpler. Moreover, in prime degree algorithms are much simpler, more efficient. Well, this is a separate story. Next, we want to have congruence quotients. Over number fields, strong approximation is very different from the case over Z or localization of Z. Then subgroup may have infinitely many congruence quotients different from a cell. For infinitely many maximal ideals, then subgroup may not surject on a cell. Nevertheless, we have criterion to decide when we are congruent for almost all maximal ideals, and we are capable to find this set of maximal ideals. And so, next question will be to decide whether a group is arithmetic or thin. As I told, this is semi-decidable problem. There is no justification. And this is important open problem. There are ideas. Well, Charles Miller sent us idea, but already this is a separate question. So, which is, and if group is of finite index, you will be interested to answer the question whether it is congruent subgroup. Why these groups don't have congruent subgroup property? Arithmetic subgroups are not necessarily congruent subgroups. So this is again illustration how this machinery come into the game. Let us take this Bianchi group. Time is pressing, so let us speed up. And let us take group generated by geometrists. Well, I selected A and B is here. So the question is, what is this group? Well, you can apply your knowledge of group theory, geometry, whatever. Try to answer this question. Now I will show you how our algorithms answer this question. First, you will test density. It's quite straightforward. Group is dense. When you want to find congruence quotients, again, for dense subgroup, congruence quotients define properties and structure of the group. here is our computational output. So what this table tells us? There are just 5 maximal ideals for which we don't have surjection. For all other maximal ideals, congruence quotients are the same as for SL2. Moreover, we know what are these exceptional congruence quotients, cyclic groups or 2SL cases. So we have congruence quotients. So according to our scheme, the next question is whether the group is arithmetically thin. We are in a class of actually finitely presented groups. I mean, Bianchi group is finitely presented. You can attempt to test arithmeticity, and you will end it up with nothing. Why? Because the group is actually thin. If you apply coset enumeration, it will never terminate. This is it. This is how that will look in practice. We don't have algorithm to test thinness. As I told you, highly likely it's an undecidable problem. And nevertheless, there is a method, which in practice very often works. Just take finite index subgroup with infinite abelialization. And Bianchi groups have such subgroups and not very difficult to select one. And if you're lucky and apply this simple trick, you may be able to justify that subgroup is thin. Again, this is not general algorithm. This is computational trick, which very often works to justify thinness. One quick comment. If problem is undecidable from theoretical point of view, this does not imply that in practice you cannot decide it. Again, this is the difference between theoretical algorithms and practical algorithms. It's not the same. So we don't need the last step. Since group is thin, I don't need to test whether it is congruent subgroup. Again, I stated to you, an exercise, try to apply any other methods to answer the question. That group generated by 2 matrices, 2 small matrices, 2 by 2 matrices. What is it? What is this group? Now, let me take other Bianchi group, the most popular. I selected it specifically.
I'm just going to interject because Misha has made a comment in the chat. He says, for subgroups of Bianchi groups, thinness is decidable, he says. So perhaps you can tell us more about that later. But,
Yes, this is what I discussed with him.
very good.
Yes.
Sorry.
Yes, I don't know the answer. Misha knows the answer.
Well, it is decidable.
Yes.
I know the answer. It is decidable.
Yes.
But it's purely theoretical algorithm. It's not practical.
Yes. Well, probably I forgot what we discussed. Yeah, no. It's very interesting. We should discuss it separately. Yes, yes. So, in this case of Bianchi group, I selected specifically for this workshop. So, this is a special type of Bianchi group. It's different from others. So, presentation is known. There are different, actually, presentations. This is what we selected. It's computationally was the most. So, what is special about this group? It is not free product with amalgamation, in contrast to other Bianchi groups. It has finite abelialization, just few features of this group. And at the end of the day, this group is finitely rigid. This Bianchi group got a lot of attention, exactly because it's stay alone if compared with other Bianchi groups. And methods to investigate, a lot of methods, came from low-dimensional topology. And by the way, this result actually used strong approximation property. The proof used strong approximation. So if you still have a question, do we need computer to solve mathematical problems? And I'm not talking about numerical analysis of partial differential equations. In algebra, in group theory, in geometry, yes, you need computer. So this is an example. What is an advantage to have computer? You can handle large data sets. You can process large data sets. And one situation where it is important is classification problems. These are the Bianchi groups or whatever groups over rings. So what are classification problems? Very old classification problems going back to 30s or 40s. Again, this is still an illustration before I proceed to main application. Can we classify all subgroups, say, of index 30? Why index 30? Because this is illustration. You can take index 100, 1 million. What does it mean classify? So I took up to index 30 because it is still reasonably small. You can list all such subgroups up to conjugacy, which is 126. It has nothing to do with our machinery. This is algorithms of finitely presented groups. So, but what our machinery tells us? What are these finite index subgroups? And what is the classification? So subgroups all are finite index. So what is the main question? Are we congruent subgroup or not? Because the Bianchi group does not have congruent subgroup property. 28 groups are non-congruent subgroups. Why? We have finite quotients which cannot be congruent quotients. This is a standard approach, how to justify that finite index subgroup is not congruent subgroup. And 98 groups are congruent subgroups. This is when basically our machinery came into the game. If we have ideals for which we don't have surjection, we can use them to justify that group is congruent subgroup. It has principal congruence, contains principal congruent subgroup, and moreover we can find this principal congruent subgroup. So how the output of computation will look? I did not list all 126 groups, I just select a few of them. So last column tells us whether it is congruent subgroup or not congruent subgroup. So each group is given by generating matrices. So what are groups in this table? Two groups with are non-congruent subgroups. This is the reason. We have very bad finite quotient. This group number 12 is congruent subgroup, and this is principal congruent subgroup contained in this one. And another example of non-congruent subgroup. And the same reason. I have 30 seconds to show you the main application. So, as I told you, why we need computer. So, this is result by Alperin. Again, it was used by Martin Britson for this justification of perfinite rigidity of this Bianchi group. So, Alperin classified normal subgroups up to index 960. Can we do better? Yes, we can. Let us take, for example, not 160, let us take 20,000. By 20,000, well, you can take 40,000, 1 million, whatever you wish. The method will work. So we can list all subgroups, normal subgroups, up to such index. There are 39 subgroups. But the question is, what are these subgroups? What is the structure of these subgroups? How our machinery comes into the game? There are natural classes of normal subgroups. These are principal congruent subgroups, which is kernels of reduction modulo various ideals, and also terms of derived series. So normal subgroups, such index, are either principal congruent subgroups, and these are levels of these principal congruent subgroups, which is generators of ideals, or they are terms of derived series, or groups designated by intersections of these groups, and there are 5 exceptional cases. These 5 exceptional cases also listed by generators. So what is the outcome? So this is full classification. Something what took Alperi and other of us maybe several years of hard work by hand now can be done by computer by clicking button. And moreover, our results found groups missed by Alperi. And this is the last slide. This is how the classification looks. So in summary, I demonstrated to you what is available, how it works, and go ahead to use it. It's available for free. Thank you very much for your attention. Let me make, I know I ran out of time, last vital comment. The introduction into this area was very short. But if you go online, December 2019, workshop organized by Misha Kapovich with Margulis and Sofer, I gave the longer than 1 hour expository talk for general mathematical audience on this project and what is involved and what is available. Why I mentioned it. You will hear, if you watch that video, various comments and questions. This is Misha. It was our joint talk, in fact. His comments and his questions contributed considerably. In particular, they will be useful for applications in geometry. So, sorry for running over time.
Any questions?
Found some examples that Alperi missed?
Yes.
Does this affect the work of Wrights and all?
No.
They don't.
That result is perfectly correct.
Alla, how long did it take you to produce this list on this last slide? How long was the actual computation? In minutes or in hours? Did it take just a few seconds? Few hours?
Well, I don't have it was feasible. Some computations took maybe a couple of days, but it was not done, say, we sat at computer with Alexander and he has done it. No, it was, we sit together for 2 weeks, but it's feasible. It is not weeks or months. No, the longest maybe took 24 hours. I can go back to computational output and to see runtime.
No, it's okay. It's okay.
It's
Just Just a comment that really SL2, SL2R, and SL2C, the lattices or subgroups of lattices, is really the only case where we know that thinness is decidable. So all other groups or
Yes.
we just have no idea, and or we know that it's undecidable. So there are a few cases where it's known to be decidable, namely these two, and mostly it's either unknown.
Yes, the most interesting would be to justify it just for SLNZ.
SLNZ is, I think it's still open.
Yes, I know it is open, which is, there were several tries to, Chris Hall, former student of Sarnak, had some ideas. The best ideas came from Charles Miller. He emailed us very good ideas how that can be justified. We just did not have time to do it. This is why I brought it to your attention. This is your area. Many people will be interested. But again, if problem is undecidable, that does not imply we cannot decide it in practice. I just illustrated it. This is what the art of computing is about. And this is where I refer to my collaborator, Alexander Hulpkin. I think I convinced geometers to yes.
Let's save any further questions for coffee.
Yes.
We reconvene at 1:30.